Stan Gibilisco here. I am going to get into a little bit of a discussion now in our complex number primer, which really is just a bunch of tidbits, a bunch of little bits and pieces of information to serve as supplements for a serious study of complex numbers and vectors. A book called Pre-Calculus Know-It-All goes into quite a lot of detail about those complex numbers and vectors and all kinds of things that you need to get ready for calculus. Chapter 6, which begins on page 90 of Pre-Calculus Know-It-All, the second book in the trilogy of know-it-all mathematics books that I wrote. Chapter 6 gets into complex points and vectors and complex numbers and how they behave. In the previous episode, we learned what a vector actually is. It has magnitude and direction. There's another way to portray a vector, and let's do it in the complex number plane. However, now, instead of using I to represent the unit imaginary number, we're going to use J, as most engineers do. Chances are you're a lot more likely to become an engineer than you are to become a pure mathematician, although I have great respect for them both, some of my earlier sarcasms notwithstanding. Now we're going to use J. This is also sometimes referred to as the J operator. A and B are real numbers. J is the positive square root of -1. We can define a point in a plane like this and assign it a specific value. Let's suppose we pick the point, let's just say 5 minus J4. Let me write that as an ordered pair. That point represents the complex number 5 minus J4. Now, when we're using the J operator, we put the real number multiplier after it. With the I to represent the lowercase letter I, we would write something like minus 4I, but now we're going to write minus J4. I don't know why they do it that way, but they do. They just do. So that's the way we'll do it. That's one example of a point. Now we have a vector that goes to that point from the origin. And we don't know specifically right now what the magnitude of that vector is, and we don't know what the direction is either. We can get a rough idea if we begin our angular axis going towards the right, as is customary in mathematics. That looks like it might be something on the order of 310 degrees. We don't know exactly what it is though. The length, well, we don't know. It's going to be a little bit more than 5. And it's certainly going to be more than 4. It's going to be the diagonal of that rectangle that measures 5 units going this way and 4 units going vertically up and down. Well, we can represent this vector as a magnitude and direction, but clearly we can also represent it as an ordered pair like this. That doesn't tell us the magnitude or the direction, but it does tell us the ordered pair, or the values of the complex number in terms of the real part and the imaginary part. As things work out, there is a one-to-one correspondence between all of the vectors expressed as magnitude and direction and all of the vectors expressed as ordered pairs in the complex number plane. Now we've learned a little bit of theory. The chapter will get into how to convert between magnitude and direction form and ordered pair form. The magnitude and direction form is generally called the polar form, where a vector has a length r, lowercase r, which actually stands for radius, and an angle going counterclockwise from the positive real number axis of theta. Theta being the lowercase Greek letter theta. It looks like a numeral 0 with a horizontal line going through it. Generally, you'll find these italicized in most texts, but they don't have to be. We can represent the polar form as an ordered pair theta r, or alternatively r theta. There's variation amongst the texts as to which one of these is listed first. Usually in an ordered pair, the independent variable is listed first, and the dependent variable is listed second. Intuitively, for me at least, I find it easier to think of the angle as the independent variable and the radius depending on the angle. So, some texts, however, who reverse this would say that the angle depends on the radius. That, to me, that's intuitively more difficult. But as long as we stay with the same form all the way through, we're fine. There is a one-to-one correspondence between the polar form of vectors, that is to say theta r, and the ordered pairs in the Cartesian plane, which we saw earlier, which goes with the real numbers going horizontally and the imaginary numbers going vertically. The polar, there is a one-to-one correspondence between the points, provided that we limit the angle to values that are greater than or equal to 0, but strictly less than 360 degrees, or if you want to use radians of measure, you would use, I'm sorry, that is not right. The absent-minded professor makes another boo-boo. At least I caught this before it got all the way through. But you got to be careful when you write expressions like this. At least I have got to be careful when I write expressions like this. 2 pi radians. So what we're saying is that the angle is more than 0, but less than a full circle. We generally do not want to go into negative angles, and we don't want to go around the circle more than once. If we do that, we ruin the one-to-one correspondence. Similarly, the radius values must always be non-negative. They must always be greater than 0. Now we end up in a specific case when we have the radius equal to 0, any angle will correspond to the same point, and that's the origin. In that particular situation, we also ruin our one-to-one correspondence. here's the polar plane, theta going like this, r going like that. If we stay right at the very center, the origin, where r equals 0, we can have any angle and it'll correspond to that point. So we've got an infinite number of polar values that correspond to that one Cartesian value. That's, in order to make the one-to-one correspondence work, then we have to make a restriction. We say that if r equals 0, then theta equals 0 by default. Now we have a one-to-one correspondence. So that's a theoretical setup. We have two different ways of expressing complex numbers and complex number vectors. It's a semantical thing. What's the difference between the complex number point and the vector going out from the origin to that point? Well, the point is just one way of expressing that complex number, and the vector is another way. The complex number is the same in either case. It's just like we're talking about, say, oh, I don't know, a library in English would be biblioteka in Russian. There are two different ways of expressing the same thing, a library, just different languages. Vectors come in very handy in engineering applications, particularly in electricity, when we talk about capacitive and inductive reactance in combination with resistance. Vectors come in very handy in navigational situations where we want to account for the lateral wind, for example, when we're flying an aircraft, or a lateral current if we're sailing a boat. All that said, now we know basically what a complex vector is, or a complex number vector. There are two forms. The polar form, which is the radius or magnitude and direction, and the Cartesian form, which describes the real and imaginary components in graphical terms. In the next episode, we will learn how to add complex numbers in the Cartesian form, both in terms of points and in terms of vectors. Stan Gibilisco signing off.